Good morning. Welcome to today's public workshop, Achieving Carbon Neutrality in California, a report by E3. This is the next in a series of public workshops focused on achieving statewide carbon neutrality by mid-century. My name is Maureen Hand, and I am joined by Rajinder Sahota, the Industrial Strategies Division Chief, Matt Botil, the ISD Assistant Division Chief, and my colleague Jordan Ramalingam. Today, we are looking forward to sharing the results of a study conducted by Energy and Environmental Economics, better known as E3, to explore ways California could achieve carbon neutrality. Amber Mahone and Gabe Montaigne with E3 are joining us today to present the study. After Amber's presentation and a few questions from me, the audience will be able to ask questions. To ask a question during the Q&A session, click the Raise Hand button in the GoToWebinar control panel. Jordan will individually unmute attendees with their hands raised so they can ask their question. All attendees are, by default, muted upon arrival. Please remember that any questions asked will be included in the webinar recording, which will be posted on our website. Written comments will be received for 3 weeks until September 9th. The link to the comment docket is on the Carbon Neutrality Meetings and Workshop webpage that is at the link on this slide. The docket will not be monitored during this workshop. The report and the presentations that are shown today are also available at the link on this slide. As you may recall, AB 32 and SB 32 established ambitious greenhouse gas emissions reduction targets of reaching 1990 levels by 2020 and 40% below 1990 levels by 2030. The 2017 scoping plan laid out a cost-effective and technically feasible path for achieving the 2030 target. These targets are milestones on the path to our ultimate goal of deep decarbonization by mid-century. Executive Order S-3-05 established a goal of achieving 80% greenhouse gas emissions reductions by 2050. But the science tells us we need to do more and we need to do it faster. The blue dotted line shows that if we were to carry forward the rate of reductions to achieve the 2030 target, we could achieve the 80% below 1990 levels greenhouse gas reduction goal 10 years ahead of the executive order. The concept of carbon neutrality is relatively simple. To ultimately stabilize the climate, the carbon dioxide and other greenhouse gas emissions generated by sources such as vehicles, power plants, industrial processes, and natural and working lands must be less than or equal to the amount of carbon dioxide that is removed from the atmosphere. The IPCC's special report, released in late 2018, finds that to limit the global temperature increase to 1.5 degrees Celsius, we need to achieve carbon neutrality globally by mid-century to avoid the worst impacts of climate change. We believe it is a priority to mitigate emissions from sources to zero where possible. Importantly, moving away from combustion of fossil fuels will result in public health benefits. And all efforts are exhausted, should we look to sequestration options to compensate for any greenhouse gas emissions left in the economy? We will use the next scoping plan update to lay out the path to achieving carbon neutrality by 2045. In 2020, there are several building blocks that will occur before we begin the formal scoping plan process. We began this carbon neutrality workshop series in early 2019, and to date we have hosted 8 public workshops focused on carbon neutrality in different sectors. Our objective has been to bring together experts to facilitate public discussions about economic, technological, and social considerations for each sector. Multi-agency efforts aimed at planning for 100% zero carbon electricity by 2045 and carbon neutrality in the transportation sector will be completed later this year. We will provide an update to the board at the end of this year on key findings from these multiple efforts. CARB will formally initiate the scoping plan process in early 2021. This will include convening the Environmental Justice Advisory Committee. We will transition from carbon neutrality workshops to scoping plan workshops when the formal process is initiated. This will also include community meetings. We plan to complete the draft scoping plan in early 2020. The target for completion of the final plan is towards the end of 2022. I mentioned interagency collaborative efforts underway that are building blocks to support the next scoping plan update. Under AB 74, Cal EPA commissioned 2 carbon neutrality studies focused on how to reduce demand for fossil fuels in transportation and how to manage the subsequent decline in supply. Researchers from UC Davis and UC Santa Barbara are conducting these studies. SB 100 charges the CPUC, CEC, and CARB with planning for 100% of total retail sales of electricity in California that come from eligible renewable energy resources and zero carbon resources by the end of 2045. SB 1440 requires the CPUC, in consultation with CARB, to develop targets for increasing biomethane in gas pipelines. And efforts to reduce emissions from natural and working lands continue. These efforts reflect a growing consensus that in order to achieve our climate and air quality goals, California must reduce and replace fossil fuel consumption across all sectors. To continue the conversation with stakeholders with some quantitative analysis, we contracted this study with E3 to assess technology and fuel transformations that would be required to reduce greenhouse gas emissions at least 80% below 1990 levels by 2045. This study focuses on the alternative fuels, including clean electricity, that may be available to decarbonize every sector of the economy. This study provides an initial assessment of the level of mitigation that may be technically possible in each sector. I want to stress that the scenarios considered in the next scoping plan will need to be more stringent than greenhouse gas emissions reductions of 80% below 1990 levels by 2050, because we are trying to achieve carbon neutrality by 2045 and limit all emissions in the system to the maximum extent feasible. As we transition to the scoping plan update, we will be considering carbon neutrality comprehensively, incorporating emissions sources and sinks from our natural and working lands. We will convene the Environmental Justice Advisory Committee to solicit feedback and consider how to maximize air quality co-benefits in heavily burdened communities. And we will also explore the economic and environmental trade-offs of pathways to achieve carbon neutrality. The technical study that we're discussing today sought to answer several questions related to deep decarbonization in California. The study addresses fuels and technologies that can mitigate emissions from the most difficult sources. It highlights trade-offs between emission mitigation and carbon dioxide removal. It compares scenarios in terms of fuel combustion, which is associated with air quality impacts that have health consequences, and risks of achieving the intended climate change mitigation and technology adoption and implementation risk. It also identifies least regrets fuels and technologies that can be implemented now, but that put us on the path to carbon neutrality by mid-century. So this workshop and study is meant to start the conversation and get us all thinking about the deep decarbonization effort that lays ahead of us over the next 25 years. Amber, thank you for joining us today to share the results of this study. I will pass it over to you for the presentation.
Great, thank you, Maureen. Can everybody see my screen and hear me okay?
Yes, please go ahead.
Great. Well, good morning, everyone. My name is Amber Mahone, and I'm a partner at E3 Energy and Environmental Economics, which is a consulting firm based in San Francisco. We have offices in Boston, New York, Calgary. I'm actually calling you today from Santa Cruz, where I am looking out my window at falling ash from the fires, which is a good reminder today that even amidst this remote workshop where we're all in our homes from COVID, climate change marches on and is an ever more important topic for us to consider and work on. So I'm excited to present these draft results to you today. As Maureen mentioned, I'm joined by my colleague, Gabe Mantegna, who can help with the questions at the end. And I was also supported by a great team at E3, only a few of who are listed here on this slide. So I'll just give a quick overview of the study purpose, the background, and then we'll jump into the 3 scenarios that we evaluated as part of this work, talk about key findings and next steps. And there's some appendix slides that are posted on the ARB website if you want to look at some of the additional sector by sector details. So the context for this study is carbon neutrality in California by 2045. There's many elements around achieving carbon neutrality, whereby emissions are offset by carbon sinks, resulting in net zero emissions. This study is focused on just the one piece of that puzzle, which is the energy and non-combustion greenhouse gas emissions. We're not taking a deep dive at cost and options for carbon dioxide removal, also referred to as CDR, and we're not encompassing or incorporating either emissions, sinks, or sources from natural and working lands. We're really focused on the energy system and the technology transformations that could support achieving carbon neutrality. Maureen already highlighted some of the key study questions. I'll just mention that some of the trade-offs that we're considering look at different levels of fuel combustion in the different scenarios, because that has implications for air quality and health impacts. We're also considering climate change mitigation risk as one of the different lenses that we can look at for risk, as well as technology adoption and implementation risk. And this also helps us to identify potential least regret strategies that will help us achieve carbon neutrality. So just a little bit more about the project context and background. This study is building on some prior work that E3 has done with California state energy agencies. In 2017, we supported the Air Resources Board and the development of their 2017 climate change scoping plan that looked at strategies to achieve the state's 2030 climate goals. We built on that in some work that we did for the California Energy Commission as part of a EPIC research grant, looking at scenarios out to 2050. And then we sort of further built on that in a more recent study that was doing a deep dive into decarbonization of retail gas in California. So this study is building on a high electrification scenario that in our previous work we identified as one of the lower cost, lower risk strategies that could help the state meet an 80 by 50 GHG reduction strategy. We also include a literature review in the report, which I won't talk about in depth here, but if you look at the report, you'll see some of that context that helped inform this research in these scenarios. The modeling framework that we use for this work is called Pathways. It's an economy-wide energy systems model of California's energy demands at a pretty granular level. We look at technology by end use in buildings and transportation. We look at energy consumption overall in industry. And we have a representation of electricity generation at an hourly level. And we also have a zero carbon fuels supply module where we're looking at particularly low carbon hydrogen and biofuels. So there's more information about this modeling framework in some of our prior modeling reports. But the important thing to know about this tool is that it's a scenario-driven model. It's not optimizing based on somewhat speculative assumptions about future costs. It's really helping us to test out different potential futures. And this slide shows the 3 scenarios that we're evaluating in this work and what those look like in terms of statewide greenhouse gas emissions. So you can see between 2020 and 2045, there's a bit of a separation in terms of emissions between the three scenarios. The high CDR, or high carbon dioxide removal scenario, achieves an 80% reduction in energy system and non-combustion greenhouse gases by 2045. The balanced scenario achieves an 87% reduction by 2045, and the zero carbon energy scenario achieves a 92% reduction. And the remaining emissions then need to be reduced through carbon dioxide removal strategies in order to achieve net zero by 2045. You can also see from this figure that the zero carbon energy scenario achieves deeper emission reductions in 2030, getting to a 45% reduction, which is actually going beyond current state statute. So this is kind of the range of scenarios that we are exploring. And again, each of these scenarios is building off of a high electrification scenario as the starting point, and then we're layering on additional greenhouse gas mitigation strategies for each. And I'll talk on the next slide about what those strategies look like. So just a little bit more background about the scenarios. The high CDR scenario has a broad range of decarbonization strategies, including energy efficiency, electrification, low carbon fuels, zero carbon electricity, and reductions in non-energy GHG emissions. But as you saw on the previous slide, it has the highest resulting gross emissions from energy and non-combustion sources, and therefore has the highest reliance on carbon dioxide removal of the three scenarios that we evaluate. The zero carbon energy scenario is the other end of the spectrum that we're evaluating. It involves faster and more complete electrification, as well as the addition of more emerging strategies for emission reductions, including the use of synthetic natural gas in the pipeline, electric aviation, fuel cell trains. Basically, we're throwing everything at this scenario that we can think of, essentially, in order to eliminate fossil fuel emissions by 2045. So the only remaining emissions in that scenario are coming from non-combustion sources, which we'll talk about in a little bit more detail in the next slide. And then the balanced scenario is in between the two previous scenarios that I discussed. So it has less reliance on carbon dioxide removal, slightly slower electrification, slightly less reliance on some of those emerging technologies like electric aviation or synthetic natural gas than you see in the zero carbon energy scenario. So just to give a flavor of what's in the balanced scenario in terms of the timing, this figure shows in gold the greenhouse gas reductions or the resulting greenhouse gas emissions for that scenario. And then the gray dotted line shows the additional carbon dioxide removal that would be needed to achieve net zero by 2045. So in all of the scenarios, there's a big ramp up of electric vehicles, energy efficiency in buildings, electric end uses in buildings as well. What we're seeing is that by 2030, we achieve high levels of energy efficiency in buildings, as well as high levels of renewable generation. There is about 75% of generation being served with renewable energy in this scenario. By 2035, we're getting to 100% sales of heat pumps in both residential and commercial buildings, as well as 100% sales of zero emission vehicles in light duty vehicles and medium duty vehicles, 93% in heavy duty vehicles. And then by 2045, in this scenario, we have fully decarbonized industry using a combination of hydrogen, carbon capture and sequestration, and electrification. There's a strong reliance on zero carbon fuels, including biofuels used for renewable diesel, renewable jet fuel, renewable natural gas in the pipeline. And we're also getting to 100% zero carbon generation in electricity. This slide has more detail about each of those assumptions, and I won't walk through all of these numbers. It's a lot. The details are in the report for your reference, but some of the things that I will highlight is that there is a reliance on hydrogen in the pipeline in all three scenarios. There's additional hydrogen in industry and trucks in the balanced and zero carbon energy scenario. All of the scenarios have the same level of energy efficiency in buildings, which is reflecting a pretty aggressive implementation of energy efficiency. The scenarios vary in terms of the year at which they achieve 100% sales of electric technologies, and that applies to both buildings and vehicles and transportation. So you can see that in the high CDR scenario, we're getting to 100% sales of electric appliances in buildings by 2040. That number is 2035 in the balanced scenario and 2030 in the zero carbon energy scenario. So it's getting more aggressive as we move from left to right in this table. All of the scenarios achieve aggressive reductions in high global warming potential gases and non-energy emissions, but we don't believe that we can fully eliminate those emissions, at least given what we know today about technology options there. So what does this look like in terms of electric loads, electric generation? This is a comparison of each of the three scenarios in 2045 compared to electric loads today in 2020. And you can see that the electricity demand in buildings doesn't change that much across the scenarios. It gets a little bit higher as we move from left to right, but there's big increases in incremental loads coming from new sources of electrification. And that's coming from vehicles, light duty vehicles, medium heavy duty, other transportation electrification, as well as in industry, from industry electrification. There are additional electricity demands associated with direct air capture that might be needed as one of those options for carbon dioxide removal, but we're assuming that that would be powered with off-grid energy, and so is not reflected here. Same goes for hydrogen production to serve industry. That's assumed to be produced with off-grid power, but there's also a lot of electricity required for electrolysis for producing electrolytic hydrogen. So overall, we see about a 50 to 90% increase in total electric loads across all three of these scenarios. This figure shows a comparison of low carbon fuels between the three scenarios. And you'll see that the biofuels are shown in green. The biomethane is the lighter green, liquid biofuels being renewable diesel, renewable gasoline, or aviation fuel are shown in the darker green. There's about the same amount of biofuels in all three scenarios. We're essentially using the total maximum supply that we think California could have access to, including imports of advanced biofuels from other parts of the country. And then there's also hydrogen in all three scenarios. You can see in the high CDR scenario, that's hydrogen that's blended into the gas pipeline. In the balanced and zero carbon energy scenario, there's additional hydrogen being used in industry through dedicated pipelines, allowing industry to get to 100% blends of hydrogen in some cases, as well as hydrogen use in the trucking sector, particularly for heavy duty trucks. So here's a figure that shows what this looks like in terms of total greenhouse gas emissions for the three scenarios compared to today. And you can see that in all three scenarios, there are deep reductions coming from every sector. In the zero carbon energy sector, we've eliminated all fossil fuel emissions. So the 33 million metric tons remaining by 2045 are all coming from high global warming potential gases and non-combustion greenhouse gas emissions. So those are things like fugitive methane for non-combustion and fluorinated refrigerant gases for high GWP gases. There's some remaining emissions, about 10 million metric tons remaining in electricity in the high CDR scenario. In the other two scenarios, electric emissions are fully eliminated by 2045. This gives kind of a direct comparison of how much reliance on carbon dioxide removal we see in each of these three scenarios, ranging from 80 million metric tons in the high CDR scenario to 33 million metric tons in the zero carbon energy scenario. We can also compare the scenarios on the basis of fuel combustion, and that's an important metric when we're thinking about air quality and human health. Now, as part of this work, we didn't do a detailed air quality assessment. In fact, we didn't do an air quality assessment at all, but we still thought that it was useful to report total fuel combustion as a proxy for what kind of co-benefits we might see from these reductions, these big reductions that we're getting in all the scenarios in total fuel combustion. You'll see that there is actually still some fuel combustion even in the zero carbon energy scenario, and that's coming from combustion of either biofuels or hydrogen. The little bit of natural gas that is being combusted in the zero carbon energy scenario has carbon capture and sequestration associated with it in the industrial sector, which is why that we can see that this scenario is getting to zero fossil fuel emissions, but it's not able to fully eliminate all combustion sources. So there's kind of a range that we see there, but again, in all cases, big reductions in fuel combustion relative to today. We can also compare the scenarios on the basis of technology adoption and implementation risk. And the big trade-offs that we're seeing here are in the high CDR scenario, there's an implementation risk really around the large amounts of carbon dioxide removal that would be needed in that scenario in order to achieve carbon neutrality by 2045. The zero carbon energy scenario has less reliance on CDR. It doesn't eliminate the need for CDR entirely, but there's a higher technology adoption risk there because it entails faster and earlier electrification, as well as reliance on less commercialized carbon mitigation strategies. So the balanced scenario is somewhere in between those two kind of bookend scenarios in terms of implementation risk of CDR and technology adoption risk in terms of direct carbon mitigation strategies. In this figure, we illustrate a risk framework where we can sort of see the different risks between each of these three scenarios. And the three criteria that we're evaluating are fuel combustion. And you can see that, as I presented earlier, the balanced scenario is in the middle between the zero carbon energy scenario, which has the lowest fuel combustion, and the high CDR scenario, which of the three has the higher fuel combustion. In terms of climate change mitigation risk, we also see the balanced scenario in the middle here. The zero carbon energy scenario achieves faster and earlier greenhouse gas reductions in 2030 and deeper reductions by 2045. So it has the lowest cumulative greenhouse gas emissions of the three scenarios evaluated, which is important when we're thinking about reducing the risks of climate change. The balanced scenario, again, is in the middle of these three scenario options. And then likewise, the balanced scenario is in the middle in terms of technology adoption and implementation risk, because again, it has less reliance on CDR as well as less reliance on technology adoption. We also took a look at greenhouse gas mitigation costs. And what you'll see in this figure is a range of cost per ton of greenhouse gas mitigation strategies. The two options at the top there are negative emission technologies, so bioenergy with carbon capture and sequestration and direct air capture. These are forms of carbon dioxide removal and would be among the strategies that could be considered to achieve carbon neutrality by 2045 in any of the 3 scenarios that we evaluated. The strategies shown below the gray dotted line are strategies that result in direct reduction in fossil-related greenhouse gas emissions. And the color codes there show the options that are included in all scenarios. The gold, or in green, the gold show options that are included in the balanced and zero carbon energy scenarios. And then the most expensive options are only included in the zero carbon energy scenario in order to ensure that we get to zero emissions from fossil fuel sources. So you can see there's quite a range here. And at this point, given the uncertainties, we can't conclusively say of the 3 scenarios that we're evaluating which scenario might be lower or higher cost. There's just too much uncertainty here. And the higher reliance on CDR strategies in the high CDR scenario kind of offsets the higher reliance on mitigation options in the zero carbon energy scenario. So looking that deep at carbon reductions that far into the future, we can get some indicative estimates of the cost of carbon mitigation through this work. So coming to some of the key findings, some of the least regret strategies for getting to carbon neutrality that we see across all 3 scenarios include energy efficiency in buildings, industry, and agriculture, widespread transportation and building electrification. We see that as being, again, among one of the lower cost, lower risk options for reducing greenhouse gas emissions. We see that in our 80 by 50 scenarios, and even more so when we start considering carbon neutrality scenarios. Zero carbon electricity is another important complementary strategy to electrification, and the ability to pair zero carbon electricity with electrification gets us kind of some synergistic carbon savings between those 2 measures and those 2 strategies, which California is already encouraging. In all of the scenarios, we see a need for zero carbon fuels, and that's needed in hard to decarbonize sectors, particularly in industry, where electrification doesn't work in all applications, but potentially also particularly in heavy duty trucking, and in achieving zero carbon electricity. So there's still quite a bit of uncertainty around the supply and cost options among the zero carbon fuel strategies, between biofuels and hydrogen particularly. So this is a place where more information, more market discovery will be useful as we start to move down this path towards decarbonization. In all scenarios, we also see a need for reduction in non-combustion emissions, and that's in the form of reducing fugitive methane emissions. That's in the form of reducing emissions from high global warming potential gases, like refrigerants. Again, we don't see that those will be possible to fully eliminate by 2045, but they represent such a large source that we'll need to make progress on those over the next 2 decades. And then finally, we see a need for investment in research into carbon dioxide removal technologies and strategies. Even in the zero carbon energy scenario, which was the most ambitious of the scenarios that we evaluated, we still see a need for some form of carbon dioxide removal. And that could take many forms. And again, it wasn't the focus of this study, but that could include negative emission technologies, such as direct air capture or bioenergy with CCS, as 2 examples. So the next steps on this report, we look forward to receiving your comments on the draft report, and then we will finalize it for consideration by the Air Resources Board. As Maureen said, this is just one piece of the puzzle that will go into the ARB's consideration as they move towards the development of the 2022 scoping plan. We do identify as part of this work some areas for further study. We think that looking at ways to maximize co-benefits, combining reductions in fuel combustion to reduce fossil fuel emissions and air pollution is one component of that, to alleviate some of the impacts on heavily burdened communities. There's also large infrastructure implications in any of these three scenarios that we've evaluated. And that ranges from the high levels of renewable energy development that we're seeing as being necessary to support decarbonization of the electric sector and support those higher levels of electric loads that we see from electrification. There's also infrastructure development associated with hydrogen production in the form of electrolyzers to produce the hydrogen, renewable generation to power the electrolyzers, hydrogen distribution infrastructure to get the hydrogen from the site of production to the point of consumption, as well as infrastructure requirements associated with powering direct air capture, with carbon capture and sequestration, and considering the trade-offs of that with other uses for natural and working lands as a carbon sink. Next, there's a wide range of potential adoption challenges that will need to be overcome in order to achieve these high levels of vehicle and building electrification adoption numbers that are considered in these strategies. Distribution and transmission upgrades could be needed to match that growth in electricity demand. But this is really in many ways about consumer decisions around the vehicles that people are purchasing, the appliances and end uses in homes. So there's a wide range of questions around how to turn the corner on consumer adoption there. And then finally, as I mentioned, that we have carbon dioxide removal strategies in all of these scenarios. And so we'll need to consider strategies to start furthering the development of some of those advanced mitigation strategies for CDR, but also for some of the more advanced forms of low carbon fuels, be they advanced biofuels or hydrogen. So those are just a few examples. This is a big transformation that we're considering for California's energy economy over the next 25 years, a very necessary one from the perspective of mitigating the worst impacts of climate change, but certainly a major transformation across every sector of the economy. So with that, I'll turn it back to Maureen to ask some questions and discuss the next steps on audience questions.
Great, thank you very much, Amber. That was a very interesting presentation, and it certainly gives us a lot of information to think about. I do have a few questions for you before we open it up to the participants in the webinar. So when you're thinking about these scenarios, how do you determine the pace of electrification in building and transportation sectors, and how does that relate to the decarbonization of the electric sector overall?
Yeah, that's a great question, Maureen. And it's one that I get often in other jurisdictions as well that are looking at decarbonization, where there's this question of, should we decarbonize the electricity sector first and then turn to electrification so that we're powering all of our electric vehicles with decarbonized electricity? And what we've seen time and again in California and in other jurisdictions is that we need to do both at the same time in order to meet these aggressive climate goals. So California is in a relatively fortunate position in that our electricity sector is already well along on the path towards decarbonizing. We've made huge strides towards reducing our reliance on imported coal. We've made big progress on increasing the level of renewable development in the state. And so, sorry about that. So there's a need to do both at the same time. Now, to your question about how do we think about the pace of electrification in the different scenarios, what we're really doing, I would characterize it as a backcast. So we're working backwards from the 2045 climate goal, and then considering, well, how quickly would we need to start turning over the building stock or the vehicle stock or the end use equipment stock in order to achieve the goal that we want by 2045, because our overarching framework is to try to replace vehicles or equipment at the end of their useful life. So the stock rollover that I mentioned is driving the pace of electrification in these scenarios. So that's how we end up getting to, say, 100% of new sales of vehicles by 2030 or 2035 or 2040 in each of the scenarios, is working backwards from our goal.
Thank you. So another area that you discussed and that we're interested in is how do you think about end uses for the biomass-based fuels in these scenarios?
Yeah, that's a good question as well. Maybe I'll go back up to the slide that showed the biofuels. So as I mentioned on this slide, there's a similar amount of biofuels in all of the scenarios, because we're assuming that we're maximizing our reliance on the availability of biofuels to California. And then the question just becomes, how do you allocate those biofuels? So the biomethane goes into the gas pipeline, and that can then be used to decarbonize industry or to decarbonize buildings to the extent that we haven't fully electrified buildings. And then the liquid biofuels can go to transportation. In the zero carbon energy scenario, that ends up being primarily going towards aviation. But in some senses, it doesn't matter that much really where the biofuels are being allocated, just that they are mitigating greenhouse gas emissions from fossil fuels in these scenarios. And there's a good amount of uncertainty still around the relative mix or reliance that we might see in California and in other jurisdictions, honestly, between hydrogen and biofuels, because these are emerging technologies, and we don't yet fully know how the cost curves for each of those will compare. We could end up seeing greater reliance on one or the other. In our work thus far, we're seeing that there is some potential for biofuels that are lower cost than hydrogen, but the cost of hydrogen is also potentially changing rapidly and coming down quickly as the cost of renewables and electrolyzers gets cheaper. So I hope that helps answer your question.
Certainly, thank you. And actually, my next question was a little bit about hydrogen. So you might have answered it, but I don't know if you have anything else to add about, again, when you're looking at these scenarios, how do you think about the role of hydrogen?
Yeah, that's a great question as well. And so what we've seen in some of our other research, where we've been doing a deep dive into decarbonizing the electricity sector in particular, is that hydrogen could play a particularly valuable role as a form of long duration energy storage on the grid to help decarbonize that last 5% or so of the electric sector that needs some form of a firm generation capacity to ensure electric reliability. But that could also be provided by biomethane, which is another form of energy storage, so to speak, in the sense that you can store that as well. So the way that we think about these scenarios is essentially we're first doing as much energy efficiency as we can in all sectors, and that goes for industry, for buildings. Then we think about, how fast can we electrify, or what do we think can be electrified, knowing that there's efficiency embedded in that electrification. Usually, to the extent that we're relying on heat pumps in buildings that are much more efficient than direct combustion of fuels, or relying on an electric drivetrain in vehicles, which is much more efficient than an internal combustion engine. And then you're left with some remaining fossil fuel emissions. And there we first sort of fill that in with the low cost options for biofuels that we see available. And then we start adding in hydrogen to the extent that we need to reduce remaining emissions. And so that ends up being primarily used in industry and in trucking.
Okay, thank you. Okay, one more question. So what are some of the trade-offs between these different paths to carbon neutrality, and how can we think about balancing them?
Yeah, that's a great question. And I guess I'll go to this slide to help illustrate that. We see trade-offs in terms of reliance on carbon dioxide removal strategies versus less reliance on carbon dioxide removal strategies as one of those trade-offs. And getting to, say, the zero carbon energy scenario, which has less reliance on carbon dioxide removal, also entails faster and more ambitious deployment of zero carbon energy strategies like electrification or hydrogen or biofuels. So there's I think questions about just how far and how fast can we push the energy systems transformation, and to get to the zero carbon energy scenario, you push that as fast and hard as you can to mitigate your risk or your reliance on CDR strategies. I guess another way to answer your question, Maureen, is to go to some of our risk considerations. Greenhouse gas mitigation risk is, I think, one of those important factors to consider when we're looking at trade-offs between scenarios. But so is fuel combustion because of its impact on human health and air quality in particular. Likewise, technology adoption and implementation risk is important. But I think as you move towards the development of the scoping plan, you'll also be considering other factors that you mentioned in terms of bringing in the environmental justice perspective and impacts to local communities. So there's really, I think, a pretty wide range of considerations and trade-offs to keep in mind.
Thanks, Amber. So I guess now we're going to take some questions from the audience. I'm going to turn it over to Jordan Ramalingam, and he will coordinate with people who have raised their hands. So maybe, Amber, if you would go again to your last slide, which had those instructions. There we go. Okay, Jordan, thank you.
Thanks, Maureen. And yes, as a reminder to the audience, if you'd like to ask a question, click the raise hand button in your GoToWebinar control panel, and that will show up on my side, and I'll call on people with their hands raised and enable their microphones from my end. So our first question will be from Tim Sassin. Tim, I've enabled your mic. You can now go ahead and ask your question.
Hi, thank you. Am I coming through?
We can hear you.
Okay, great. Thank you. Tim Sassin, Market Development Manager for Ballard Power Systems. Thank you very much for doing this study. Love the work that E3 does and have a lot of respect for your technical expertise. I'm wondering about how to contextualize this study. It does a good job of assessing the three scenarios that you've presented. What's interesting also is finding out how those three scenarios were constructed, as in what led to the different allocations of the different types of technology to the different sectors. For example, we see hydrogen applied to heavy-duty trucking, but not in medium duty or material handling or in other sectors. There's a certain percentage, 5% allocated to mixing in with the pipeline. That could be varied. How were those scenarios constructed, and how should this report then be used to inform the policies of California? Thank you.
Yeah, thanks, Tim. That's a great question. So the scenarios are constructed by us, and we're really making a whole bunch of decisions in each sector, considering what we know today about cost, what we know today about feasibility, what we know today about commercialization. So, for example, you asked about hydrogen in end uses, and I'll just maybe go back up to the table that shows some of the differences between the scenarios. So there's a 5% blend of hydrogen in the pipeline because, according to our research, that can be achieved today without any major replacement of the existing gas distribution pipeline, and so it's a blend that we think is feasible without major changes to the gas distribution infrastructure. But we do apply up to 100% hydrogen in some industrial processes in the balanced and zero carbon energy scenario, because we see that as a very feasible way to reduce emissions, albeit with a cost associated with it. To your question about medium and heavy duty trucks, again, there we're making some professional judgment assumptions about the range of cost options and commercial technologies available today. So if we kind of go to the cost per ton of the different options, the modeling framework that we're using is not a least cost optimization tool. So it's not, the model doesn't pick for us the measures, we are picking those. But those choices are informed by our understanding about where those costs may head, in the next 25 years, which of course is pulling out a crystal ball and trying to, make some pretty speculative assumptions around how technology costs could change over time. But our analysis at least is showing that, for example, medium duty vehicle electrification is among one of the lower cost technology options available. And so that is why you see that in all three scenarios as something that we're relying on pretty heavily. We also see the potential for heavy duty electrification to be relatively cost effective by 2045. And so that's included as well. Heavy duty hydrogen is kind of within that same range. So essentially, we don't know today how those costs will play out. We see the potential for hydrogen fuel cell trucks to be particularly competitive in the long haul heavy duty trucking sector, and heavy duty electrification to be more applicable for some of the more shorter distance heavy duty applications. So
I guess
does that help?
It does, and there's nothing wrong with educated assumptions as long as a report like this is very clear about what assumptions are being made and where there's sources for the information, where those sources are coming from. So I hope in the final report there's a lot of clarity around that. And what also feeds into this conversation for decarbonization and cost, you said this is not a cost optimization tool, so maybe it's another study, but it's a question of energy carriers and building out infrastructure to suit energy carriers, mainly those electricity energy carriers are built out of the grid to suit the electrical load shown versus build out of, for example, hydrogen infrastructure. And where does that trade-off come in when you apply hydrogen for capturing renewables or for delivering energy to dense areas versus building out grid infrastructure? The cost impacts could be very large and the timing for when to make those investments could be very near term, considering the long life of those. So just wondering, is that a component that you're considering to add into this study, or is there a study that's coming that will assess that?
Yeah, I mean, that's a complex and deep topic. You know, I would say we're not planning to do a really deep dive into, you know, associated hydrogen distribution infrastructure. We do make some assumptions around, for example, dedicated hydrogen pipelines to industry. So, you know, there's some embedded in there. But I would say, you know, if we're missing something really important, or, you know, if you're kind of getting at something that we've missed, please, you know, flag that to us in your comments, and we'd love to take a look.
Thank you.
Great. Our next question will be from Bud Beebe. Bud, you can now ask your question. And Bud, it looks like you need to unmute yourself.
There we go. Yeah, I've clicked
it.
Sorry. Hey, yeah. So this is a great study, a good place to begin to understand a lot of the options. Thank you so much for working hard on this. California is not an energy island, and I know this is done for California studies, but surely you have incorporated broad energy reach throughout the Western region, WEC, Canada, and so forth. As you consider that, I think it would be helpful to include within your scenario qualitatively initially, and then as it's become clear, you can add to that electric transmission is not the only way that we can get clean carbon-free energy across geographic areas. Hydrogen pipelines will do wonderful service in that way. So, for instance, if we want to increase the amount of clean energy that comes from Canada, or even say from the Washington, Oregon area, rather than trying to bring it down through electric transmission, portions of this can well be done with a hydrogen dedicated pipeline. I'd caution that you not try and put it into a methane pipeline or mix it with methane, because methane is in fact a carbon emission source. So we can make it neutral with other ways, but it's going to remain a problem. So just think about including hydrogen only pipelines, which are pretty cheap to put in, pretty easy to put in, relative to electric transmission, especially new electric transmission. So appreciate it if you'd consider that. And then just a second, oh, go ahead, yeah.
Oh, I was going to say, yeah, thank you, Bud, for that comment. And that's absolutely something that we've been thinking a lot about. And I will say that it's somewhat implicit in our hydrogen scenarios for the balanced and zero carbon energy scenario, in that the industrial hydrogen, which is a fairly large portion of the total energy consumption in those cases, is assumed to be produced with off-grid power. And so that could be that the hydrogen production is occurring anywhere in the world, most likely somewhere in the West, and could then be piped into the state. That in our research, that is one of the lower cost ways to produce hydrogen, is to produce it with off-grid solar or wind, you know, store it somewhere and then deliver it to the end users with pipes. So we're absolutely not assuming that all of that hydrogen is produced within California's borders as part of this study. And I agree with you, and I think also with Tim, we could make that sort of implicit infrastructure assumption more clear in the description of those scenarios.
Super. I think that'd be a great thing. Just a second item too, and that is that electrolysis, although it's a very mature technology, no problems with electrolysis for making hydrogen. But when we consider biofuels, even though they're ultimately limited, It's a big source and an important source for California. And of course, you don't have to make biofuels into electricity to make it into hydrogen. You can use steam reformation as a pathway to move those biofuels into a cleaner and negative carbon situation. What I'd like to point out, I know you know about that, but what I'd like to point out is that when you do steam reformation of methane, for instance, from biofuels, that produces a pure carbon dioxide exhaust. And that can mean much more efficient CCS of the carbon dioxide. It means that you can capture it locally, virtually as a product of the process. And of course, you probably know now that's how we get the carbon dioxide into sodas these days, that they take it off a refinery steam methane reformation. So just to make sure that that's popped, if you will, in the explanation of your scenarios. Appreciate that. Thank you.
Thank you, Ben.
Our next question will be from Suzanne Reed. Suzanne, your mic is now activated.
Thank you. I appreciate the presentation and understand the technical aspects of it. I am interested in a couple of things. One, the extent from the technical side, the extent to which individual or community off the grid generation was factored into the scenarios. And then the second may be a question more for ARB, and that would be contextually a lot of shifts are happening and work is happening at the grassroots level with communities creating their climate action plans and expanding those into sustainability plans. And I'm wondering what the perceived intersection is with those activities and ultimately the integration into the scoping plan, as well as how this study will fit in more immediately to work on the economic recovery. I know there's an economic recovery task force, and wondering how we're going to look at investment and public-private sector partnership to speed economic recovery and influence basically a green recovery in the process.
Great, thanks, Suzanne. Maybe I'll take your first question and then I'll pass it over to Maureen or Rajinder to answer your second question.
Thank you.
So in terms of community or off-grid renewables, I would say that this analysis is a little bit higher level than getting to questions around where the renewables that we're assuming are specifically cited, or whether they're community scale, grid scale, or even behind the meter. We're essentially looking at how much total solar, for example, we would need to power the grid, but we're not sort of getting at that level of detail in terms of the scale or the size of those systems. So I hope that helps clarify. And then Rajinder, do you want to take Suzanne's other question, second question?
Sure, Amber, thanks for that. And this is Rajinder Sahoda with the Air Resources Board. So I think there are two questions there. One was, how do local efforts mesh with the work at the state? And then a second question about the economic recovery piece. On the local piece, the action that happens in the climate action plan, sustainability plans, and even things related to planning decisions, those have a huge influence on GHG emissions, especially in the transportation sector. Transportation, whether it's the extraction, refining, or actual use of those fuels, accounts for over 50% of the greenhouse gas emissions in the state today. And if we don't get a handle on that sector, we're never going to achieve the deep decarbonization targets that we need. So we do have an entire division that works to consider how to work with local governments, local agencies, with OPR and CalSTA and Caltrans on how to look at that whole issue of transportation, both at the state level and at the local level. So those collaborations and the efforts and jurisdiction of the local level is going to be even more important as we move forward, because we're not going to be able to realize all of the deep decarbonization at the upstream energy supply that we're working on through our state level policies. For the economic recovery piece, you know, one of the things that we had in mind when we started this report with E3 was the next scoping plan isn't due until 2022. That's a long time to wait for the state to start sending signals about the areas in which there's interest in moving forward, especially areas that are already identified as least regret. So as proposals have been coming in, we have been involved in reviewing those proposals, but we're also using this effort here to put down indicators of things that we think are going to be important for the long-term decarbonization effort, and that there are areas that we don't need to wait for a scoping plan to start working towards. Infrastructure for resiliency of the grid, looking at charging infrastructure for electrification of the transportation sector, understanding building decarbonization. All of these areas are opportunities to start taking action today and can support jobs and economic recovery. We've certainly seen proposals by some of the energy companies that are aligned with what we're thinking about in the state long term. And in a previous workshop that I was in, I flagged that that private-public partnership is important. Our energy companies, whether it's the utilities or whether it's our fuel suppliers, they have infrastructure throughout the state. We should be considering how we can leverage those relationships to think about how that infrastructure can be used to think about a low carbon energy economy. We saw recent articles about Marathon and about P66 pulling back on producing fossil transportation fuel, but looking at renewable fuels as they move forward. And that's taking existing infrastructure, but producing low carbon energy. Those are the kinds of things that I think we need to see happen. And those are the kinds of economic recovery that we want to make sure we're sending the right signals so that people can be thinking along those lines. Thanks.
Thank you.
Okay, our next question is from Robert Larson. Robert, you can go ahead and ask your question.
Yeah, thanks very much. Well, this is an interesting report. It's obviously very high level, and there's a lot of devils in the detail issues here, but I just want to point out it's a pretty massive simplifying assumptions that no grid electricity are going to be used for hydrogen production or for CO2 capture or direct air capture or CCS. So I think at the very least, you guys ought to add some sensitivity analysis to look at the potential of a certain amount of grid electricity being used in those areas. I don't think, well, I suppose you could regulate the source of those electric power to those economic activities, but I think that's pretty impractical. But anyway, that moving a little, you know, a slider of a sensitivity on those assumptions will have a massive impact of on what you're doing, and I think you need to better resolve that if this study is going to be useful. Also like to point out, just recently, the Department of Energy at Argonne National Lab has shown a CO2 to ethanol conversion at low cost. And so when you're thinking about biofuels, I think the ability to take carbon dioxide and move it to a synthetic liquid fuel is very, very important. And I'd just like to point out the issue of handling the legacy vehicle fleet in California. There's over 14 million cars and more millions of trucks that still use combustion engines. And it's pretty long time to wait for a turnover in the car park if You apparently are just assuming that electric vehicles will eventually replace all ICE powered vehicles out there, but you know, that's a 30 or 35-year window. So either there's got to be some incentives to increase that, or there's got to be a big push on using biofuels in existing vehicles, which will deliver immediate benefits. So I think I'm going to be interested in reading the report and might have some more written comments for you later, but thank you for those questions, for taking this question.
Thanks, Robert. There's a few pieces in there. I'll try to respond to a few of them. So on the grid electricity being used to power things like direct air capture, I agree with you that that would have big implications in terms of total electric loads. And that could be something we deal with in a sensitivity. We have tried to at least quantify what the magnitude of those electric loads would be in order to give a sense of the scale. So that's certainly something that we've been thinking about and have flagged that. Let's see, legacy vehicles, and can we really turn those all over to electric? I think it is pretty clear that there would be incentives needed. This study is not really trying to get at the policies that would be needed to achieve these scenarios, but rather what the technology transformation would be. And the next step around that, of course, is what are the policies that get you there. But we do assume the use of some biofuels, particularly in medium and heavy duty trucking in some of the scenarios, acknowledging that in not every scenario do we achieve such a early and rapid transformation of the vehicle fleet. You also mentioned CO2 to ethanol as another fuel pathway, and I think that's also there's so many fuel pathways to consider. That is an interesting one. We have been looking closely at Livermore's research and taking that under consideration. So thanks for your comments.
Okay.
Okay, next we'll hear from Richard McCann. Richard, go ahead and ask your question.
Oh, I just had a quick question. I was looking at your chart that had ranked measures by cost, and one of them was achieving 100% clean energy in the grid. Third up from the bottom, electricity cost 100% clean. Is that an incremental cost, and for what? And if so, what increment of the electric load is that cost amount for? And then the second part of that question is, are you considering the is that against an alternative of using a gas peaker, or does it net out the capacity value of replacing a different type of peak resource?
Yeah, that's a great question. So Gabe can jump in and correct me if I forget some of the details on this, but my memory is that this is calculating the incremental cost of decarbonizing essentially the last 5% on the grid, going from 95% to 100% zero carbon. And the range here is represented by, we could use biomethane or hydrogen to serve that last portion, or we could add additional storage and renewables. In terms of capacity costs, for the biomethane or the hydrogen, I think we're assuming that you're able to repurpose existing gas capacity. For additional solar and storage, there would certainly be some additional capacity costs associated with that. I don't recall if we treated those in the higher end of this cost range. Gabe, does that sound about right? Am I missing anything there?
Yeah, that's exactly right.
Great, thank you.
Okay, thanks. Yeah, that helps me understand what you're calculating here, so I can assess it. Okay, thanks.
Yeah.
All right, our next question is from Sasan Sadat. Sasan, go ahead and unmute yourself and ask your question. Hi, Sasan, are you there? Okay, we're gonna go ahead and move on to Charles White. Charles, go ahead and ask your question. You will have to unmute yourself as well.
Can you hear me?
Yes, we can. Thanks, Charles.
I got a bit of an echo. I tried to submit online, but it didn't work. But here, I'll try this. So recent CARB Advanced Clean Truck Rule discussions have indicated that all new heavy-duty refuse trucks should be electric starting as early as 2026. And I've asked this question before, but it doesn't make sense given that renewable natural gas trucks are the industry's preference, which have very low greenhouse gas emissions and low NOx emissions. In addition, such use provides a means to produce low carbon RNG through the anaerobic digestion of organic solid waste, which is also a goal of CARB through the implementation of SB 1383. That is the reduction of organic waste disposal to landfills to reduce emissions of methane, a short-lived and more potent greenhouse gas than CO2. Wouldn't it make sense to continue the market demand for such RNG from organic solid waste for the longest possible times? Shouldn't the conversion to new electric refuse trucks be delayed as long as possible to enhance the use of RNG and the reduction in landfill methane emissions? Thank you.
Hi, Chuck. This is Rajinder, and I can take that question. So part of that question, we are not going to comment on today because most of the folks on this call are probably aware that a lawsuit was filed against the ACT rule. And because it's ongoing potential litigation, we're not going to comment on some pieces related to that lawsuit. In terms of landfill diversion and a useful end purpose of methane that may be captured and use of that RNG, RNG can be used in other sectors as well. It doesn't have to just be in the transportation sector. And so we absolutely want to support the efforts to remove and divert waste from landfills and find a good use for that energy, especially if it helps to displace fossil natural gas and helps to decarbonize the other sectors out there.
Thank you.
Okay, our next question will be from Sean Ebdent. Sean, go ahead.
Yeah, hello. So thank you. I think this is a good start, this report. I represent Ørsted. We are a global large-scale renewable energy developer, principally wind and solar, offshore and onshore. We are very much in support of increasing renewable electrification. And in our view, hydrogen is actually an extension of an electrification strategy. And one of the elements that we look at is to encourage an investment and to do large-scale renewable generation, whether it be wind or solar. One of the barriers that we see in certain markets, and California is no different, is the issue of curtailment and growing curtailment going forward. So in scenarios that you look at in your studies for higher electrification, how much did that come into play? Whereas with hydrogen, that does provide another route to market and perhaps a more storage solution as well, both daily and long term.
Yeah, thanks for your question, Sean. So I'll just maybe go back up to this fuels chart. So there's a really massive increase in hydrogen use, particularly in the balanced and zero carbon energy scenarios. And we didn't take a really close look at electric grid operations as part of this study. We've looked at that more closely in other work. And what I can comment on from our previous research is that the quantity of renewable curtailment in these cases is much lower than the total hydrogen demand, particularly in these two scenarios, the balance and zero carbon energy scenario. So we see a huge benefit from using electrolysis to produce hydrogen from renewables that might otherwise have been curtailed. And that certainly is one of the lowest cost ways to produce hydrogen if you can get access to that energy.
Right.
But we see that even once you sort of use up all of that otherwise curtailed renewables, there's still potentially a need for additional hydrogen. And from that, we see it being potentially most cost effective to produce that hydrogen, with off-grid renewables in a place where, you can get really high quality capacity factors for wind or solar, and then pipe the hydrogen to its end uses. So that's, I guess, the best answer I can give to the question. Right
No, well, I appreciate that, and I did like that you guys are looking at utilization of the gas pipe infrastructure. We are involved in several gigawatt hydrogen projects in Europe now that are doing the same, and to achieve the lowest cost delivered energy, it really turns out to be a hybrid of both direct renewable generation along with integration of a gas pipeline that can be electrified with electrolytic hydrogen. So the combination of the two is what seems to be driving a lot of the policy in Europe, and I'm just wondering if you see similar applications in markets in the US that you've studied.
Yeah, that's a good question, John. And we've been really carefully following a lot of those studies that have been coming out of Europe. We include some commentary on those in the literature review of our report. And yeah, absolutely, we see particularly a role for dedicated hydrogen pipelines serving industry in California. What we see being a key difference between some of those European studies and California is the climate. So essentially, in places where it's much colder, such as parts of Northern Europe, in Germany and in the Netherlands, where some of these studies are sort of the furthest along, they're seeing a role for both electrification and some use of hydrogen to heat buildings.
Right.
We see that as being sort of less plausibly economic given California's relatively warm climate, but certainly in industry and in heavy duty trucks, and then potentially as a form of long duration energy storage to decarbonize the grid. We see very promising roles for hydrogen.
Thank you. And my last question is just in relation to the cost. What we're evaluating, and we're involved in a gigastack study in UK in assessing the cost of electrolytic production, electrolyzer. And in many scenarios that we've looked at is that we see electrolytic hydrogen dropping to where thermochemical hydrogen is today, or SMR hydrogen production costs are today, and that will occur within the latter half of this decade. Just curious to see if your studies and research has come to a similar conclusion that as the scale of electrolytic hydrogen is deployed, you see the costs starting to come down rapidly.
We do see that. That's right. And whether electrolytic hydrogen can compete with fossil SMR hydrogen depends to some degree on what you think the future cost of fossil natural gas might be. But we actually just recently did some research, not as part of this work, but as part of some other research with Mitsubishi Hitachi Power Systems, where we were updating some of our hydrogen cost assumptions. We were surprised to some degree to see how much faster the cost of electrolyzers in particular may have come down even from, looking at this a year ago.
Yeah, yeah. Very good, thank you.
Okay, our next question will be from Alan Zelenka. Alan, go ahead and unmute yourself and you can ask your question.
Yeah, back on the cost comparison chart. Did you bring that up? I had two questions about that. What's the process you went through to develop these cost estimates, and what were your sources, types of sources? Did you borrow from other folks, or did you do a lot of original research?
Yeah, that's a good question. So we developed these cost estimates kind of from the bottom up based on our own research around technology costs and potential learning curves out to 2045. Obviously it's going to be a range of sources given that we're comparing everything from, trucks to industry options here. But it's, we're using a pretty simple, transparent spreadsheet to kind of build up the assumptions based on kind of our best review of available, publicly available data. It's a different set of sources, I would say, for each of these options on the figure here.
Right, thank you.
Yeah, and I can also just jump in and say there's more detail in the reports on that if you want to check that out.
Good to know, thanks.
Our next question comes from Maria Demora. Maria, go ahead.
Hi, yeah, my name is Cecilia Mora. I'm from Union of Concerned Scientists. I have two short questions. First of all, are your results going to be used in the mobile source strategy or any other CARB products? And number two, is the model and the data going to be public?
So this is Rajinder, and I can answer those questions. The first one was if the information from the study was going to be used in the mobile source strategy. That is also due towards the end of this year. We are internally coordinating closely with the divisions and the staff that are working on the mobile source strategy. And so you will see very similar types of results. They may not be exact because in the mobile source strategy, they are looking at solving for SIP targets as well as the long-term carbon neutrality. And for us, in this effort, we're looking not at SIP targets, just carbon neutrality. The scopes are also slightly different. Our scope in the study is economy-wide, so we can look for reductions across all sectors of the economy. The mobile source strategy is focused on just the transportation sector. So there will be some artifacts, just some differences resulting from the fact that the two studies are trying to get at two slightly different questions. In terms of the public model, et cetera, we are not going to be posting this version of the model or the inputs like we did for the last scoping plan. The reason for that is this was a preliminary report and effort that we asked E3 to do for us, just so that we could get the conversation started on the magnitudes of transformation that we need to see if we're going to think about hitting that carbon neutrality target in 2045. And really to highlight some of the least regret strategies so that people aren't waiting to take action. We do have a previous version of the model from the last scoping plan that only goes out to 2030 on our website, but the plan was not to post this one and it wasn't in our scope.
Thank you.
Hey, Colin Murphy, you're our next question. Go ahead.
Hi, thanks. Definitely want to echo the comments people said previously about the really useful nature of this and the quality of the work. I had a quick question on the hydrogen side, particularly in the heavy duty sector. Can you talk a little bit about the sort of amount of infrastructure investments going to be needed to support the results you had on hydrogen? And this is probably in the report itself, but if you know offhand the sort of final retail cost of hydrogen, that would be really useful.
Yeah, that's a great question, Colin. So for hydrogen infrastructure, particularly for heavy duty trucking, there's a need for hydrogen fueling infrastructure and a distribution network to serve that. In this work, we're not getting at the level of detail of really looking at, what the cost to build that out and whether it would, be along just existing trucking corridors or more distributed. I will say that in our research, there's a very big difference between the cost of hydrogen produced coming out of the electrolyzer and then the cost of retail hydrogen once you factor in the cost of building the hydrogen refueling stations, which are very capital intensive. And then, the retail cost of hydrogen to some degree needs to recoup the cost of that fueling infrastructure. And so it depends to some degree on what the utilization of those fueling stations are. If they're used heavily and frequently, you can amortize the cost of those fueling stations over more hydrogen sales. So I don't have off the top of my head what the retail hydrogen costs would be, but I will say that they're probably 5 to even 10 times higher than the cost of hydrogen production coming out of the electrolyzer. So again, we're not kind of getting at the really granular look at all of the infrastructure build out implications, other than to note that they would certainly be needed to support the refueling infrastructure. There's a similar corollary, of course, for charging infrastructure for electric vehicles, and particularly for heavy duty trucks. You may need some sort of DC fast charging, which comes with its own sort of significant electric infrastructure requirements to support. So in any of the scenarios that we would be considering, there's really large infrastructure investments required to make this happen.
Okay, thank you.
All right, our next question will be from Allison Smith. Allison, go ahead.
Good morning. Thank you very much. I have a few questions, and I'll start with a question on the cost. If you could go back to that chart. I'm wondering, oh, hold on a sec there, thanks. So I'm wondering how you develop the cost for biomass with carbon capture and sequestration. You're showing a range of 110 to 310, but the Lawrence Livermore National Lab study, Getting to Neutral, has biomass to fuel conversion with sequestration at $29 to $64 per million metric ton of CO2.
Yeah, thanks for that question, Allison. And we did review the Lawrence Livermore study, and one of the things we noted about it is a really big reliance on forest waste as the source of that bioenergy. So we ended up not actually using that resource to inform these cost estimates. I'm sorry, every time I get a chat message, my screen sharing stops. So let's see, the BECCS cost, the bioenergy with CCS costs here, we're relying on the Global CCS Institute for those cost estimates, which we found to be a very credible, robust source.
And so I just following up on that one, why do you ignore forestry waste? I mean, it's a pretty significant available resource here in California.
Yeah, so it's not that we're ignoring forestry waste, and absolutely it is a large resource in California. we just felt that the assumptions in terms of the total potential were very ambitious and may not lead to a sustainable forest resource in California. It was kind of at the far upper end of the range of forest waste potential that we've seen in our review of other literature.
Right, well, maybe we should have a further conversation on that with the experts. I had two more questions. My second one is, in the study, you've assumed 24% of building stock to either be retrofit or constructed with a high efficiency shell by 2030, and that moves up to 52% by 2045. How do you assess this turnover? Is there actual, I apologize, somebody's trying to call me. Sorry. Is there actual data that shows this kind of turnover, or is that more of a theoretical factor? And when you're assuming this high building turnover, do you assume some of the cost of building electrification is not included in your evaluation because it's already part of that retrofit?
So the building shell efficiency assumptions are applied in all of the scenarios as part of the state's effort to improve building efficiency. So this is kind of one of the input assumptions around moving towards higher efficiency buildings in California. It's a separate cost estimate from the electrification, although certainly combining electrification and building shell retrofits at the same time can lead to cost efficiencies.
Okay, and then my last question, I'm curious, and this isn't so much the pathways model, but more in how you address the electric grid and the resources that are needed. I'm wondering, how do you model the extreme weather events that, like what we're experiencing right now, where the electric grid is very reliant on natural gas generation to minimize rolling blackouts? And, you know, everybody kind of recognizes that natural gas in the near term supports that the intermittent nature of wind and solar, but the ability to ramp up to meet these extreme peaks is actually dependent on the use of line pack on the gas system. And that line pack exists on the gas system because we're moving all of this core gas in for storage for use in the winter. So without residential gas demand, the ability of the natural gas system to ramp as quickly for EG could be really difficult in the future. So how do you address that sort of extreme weather event as you're planning out into the future?
Yeah, that's a great question, Allison, and it is a really important challenge for California to address as we move towards carbon neutral futures, because we will certainly want to maintain, if not improve, electric reliability relative to what we're achieving today. So we're not doing a really detailed electric reliability study as part of this work. But what I will say is that in all of the scenarios, we have at least 5% of the total generation by 2040 that's being served by dispatchable resources. Today, that is served by fossil natural gas. In these carbon neutral scenarios, it's being served, still by fossil natural gas in the high CDR scenario, but by some form of zero carbon fuel in the balanced or in zero carbon energy scenario. So either from renewable natural gas or from hydrogen that's providing that firm resource to provide electric reliability during these types of challenging grid events.
And I guess that was why it kind of jumped out at me, because you do still have natural gas generation in the other scenarios. And really the way the system operates would be very different if you've electrified all the building appliances. So it's just something for us to consider. that the way the system operates today and the way it operates in the future is very different, and those costs could look very different as well. Can I throw in one final question? I apologize for monopolizing, but I was curious. You said that you have looked at the the Lawrence Livermore study. There are a couple of other California studies that I haven't seen mentioned, and they've been highlighted in some of the other carbon neutrality workshops. The Moniz study on optionality, and then the LADWP work with NREL. And that NREL work is actually looking at some very deep modeling and grid reliability that I think is important to inform this discussion. I think it's the most comprehensive thing I've seen, looking at how does the electric and distribution grid work under a different set of scenarios. So I do think it's important for you to look at some of that work and have some conversations with NREL and DWP.
Amber, this is Rajinder. Do you mind if I jump in for a second?
Yeah, go ahead.
So all of this work, electrification, the fuel mix that we're thinking about in the future, we're working very closely with our sister agencies, so with the PUC and CEC. This conversation here is just to get people thinking about broadly what we need to do to transform the way that we produce and use energy to see those longer term decarbonization goals. When we start to do the scoping plan, we will be digging into the kinds of questions that are being raised here, because we will have to do analyses of the economic costs of the different scenarios that we develop. And we will have to rely on the expertise at CEC and CPUC in terms of what they think is possible and reasonable, because it has to be cost effective and technologically feasible to meet the requirements for the development of the scoping plan. So I really appreciate that we're hearing about all these studies that we need to include in here, but I wanted to make sure that this study and this effort was put in the right context. It's not meant to answer every question. It's meant to actually solicit the kind of feedback we're getting here. And in terms of, what the future landscape looks like, we've already been talking about how the way that we've thought about energy policy regulations for the last 50, 60 years has to change, given that we're going to be seeing climate impacts moving forward, whether it's wildfires, whether it's rolling blackouts, or other kinds of impacts. We're going to have to plan for those and figure out how to actually have some flexibility to make sure that we don't have uninterrupted power, and that we're not also creating a situation where there's a public opposition to addressing climate policies and supporting climate policies because we can't meet basic energy needs across the state.
Thanks, Jinder. And I think, Matt, did you want to weigh in on the forest biomass question as well?
Yeah, thanks, Amber. Hi, everyone. This is Matt Potome, Assistant Division Chief at ISD. And so, Allison, just kind of going back to your first question, I did want to mention that this question about the availability of forest biomass is wrapped up in a larger question that we're looking to answer with this scoping plan, and that is, between now and 2045, what will the forest look like in California? What is the carbon that's coming in and out of the forest? What's the flux essentially from forest carbon? And what is the effect of some of the interventions that we will all have on the forest going forward? And as we think about those interventions, what do we do with that forest residual, and what are the highest and best uses of that forest biomass? And so definitely part of a larger question that we're going to continue to evaluate and we have on tap for the scoping plan, and certainly welcome folks' feedback on some of those questions as we move forward.
Okay, we have time for 2 more questions from the audience before closing remarks. So we're going to go ahead and unmute William Leedy. William, go ahead. William, looks like you're self-muted. Can you go ahead and unmute yourself? Okay, William, we can't hear you. We're going to go ahead and move on for the sake of time. Julia Levin can go ahead and unmute yourself, and you can ask your question. Okay, 3rd time's a charm. Janice Lynn, You're next on the list here. I'm going to go ahead and unmute you. You can go ahead and ask your questions.
Squeaked in there. Thank you so much. This is Janice Lynn representing the Green Hydrogen Coalition. I just want to thank ARB and E3 for this amazing study. It's definitely gotten the conversation started and super helpful. I have a few questions just for clarifying purposes. I wanted to confirm, so question one is for the hydrogen sources. I just wanted to confirm my understanding that it was assumed it was mostly electrolytic, some biomass gasification, and for the electrolytic, it was all off-grid. And I didn't in the report see any assumptions of what the mix was. I'm wondering if you could comment on that. So that's question one. Question two is, I noticed for the industrial applications, it was mostly for boilers and process heat. And I'm wondering to what extent the study looked at decarbonization opportunities to use green hydrogen to displace gray hydrogen, the commodity that's used today in oil refining is an embedded carbon in ammonia for fertilizer, sort of a swap out. And then the third question is, when you looked at, in particular, ag applications, how did you handle emissions, say, from open burning of ag waste and maybe repurposing that ag waste to make green hydrogen? So those are my three. Thank you so much.
Yeah, great. Thank you, Janice. So your first question on the mix of hydrogen, some feedback, that will help. So on your first question about the mix of hydrogen, so correct, we're assuming green hydrogen, electrolytic hydrogen, for the production. There's a mix of on-grid and off-grid. So I think we clarify this in the report at some point, but hydrogen, Gabe, you can correct me, hydrogen for transportation is assumed to be produced on-grid, and hydrogen in industry is assumed to be produced off-grid. So there's some mix there, acknowledging that we may end up with a mix. Maybe the on-grid hydrogen is used to absorb renewables that might otherwise be curtailed. The off-grid hydrogen is used to produce a lower cost form of fuel where needed. In terms of industrial uses of hydrogen, the gray hydrogen used in refineries and in oil and gas, that is an interesting one. We are assuming in these scenarios that there's basically a massive reduction in oil refining in California, commensurate with the reduction in demand for fossil fuels, essentially. So as vehicles are electrifying and the demand for transportation fuels like diesel, aviation fuels, gasoline are decreasing, that demand for gray hydrogen would be dramatically reduced as well. Now, it may be that there's, still some applications for which that could be displaced with green hydrogen. And I think we'd love to know any more details about that we could incorporate into this report. Admittedly, some of the really disaggregated information about industrial and use processes is challenging to find given some data limitations in California and elsewhere. So great point there. And then to your final question, which was about agricultural, open burning of biomass wastes. We do assume that California biomass waste and agricultural residues can be repurposed to, in this case, mostly produce biofuels. And I think we've heard from others as well that you don't need to produce advanced biofuels through, say, biomass gasification. you could instead turn that biomass into hydrogen. And again, I think that's just one of the sources of uncertainty around future zero carbon biofuels pathways or zero carbon fuel pathways in terms of what will be the best, highest use of those biomass wastes and residues, whether it's to produce hydrogen or to produce renewable natural gas or other forms of renewable liquid biofuels. So hopefully I got all of them, and that helps answer those questions.
Thanks, Amber. Okay, our last question will come from Anne Hancock. Anne, go ahead and unmute yourself and you can ask your question.
Thank you. Anne Hancock from the Climate Center, and this is a question primarily for ARB. The 2045 target frames ARB's carbon neutrality work. The 2040, but the most recent science shows that this target is far too late. Basically, 2045 doesn't match the most current science. So we acknowledge that moving this target up makes the challenge even more daunting, but just the same, we have to. So this is a two-part question. How is ARB addressing this realization that we have to move our targets up for carbon neutrality? And what's needed to update these targets to align with the most current science? Thank you.
Hi, this is Rajinder, and I can speak to both of those. So when we actually go to do the scoping plan, we get to design a suite of scenarios. And when we design that suite of scenarios, we can design an aggressive scenario, a range of scenarios from not as aggressive to meeting exactly targets that are out there in executive order and statute, and even more aggressive. So we have the opportunity to show what a more aggressive target that aligns with the science would look like. There's a target in statute right now for 2030. There are executive orders past that for 2045 and for 2050. And what we are planning for is 2045, because that is an existing executive order. That doesn't mean new statute may not come, that new statutes are prevented from coming online and actually putting into law something like a 2030 target for 2040 or 2045. Certainly that can happen. The legislature has often weighed in on climate targets and climate programs. That is their purview, and that is what we expect them to do. And so there is going to be an ongoing conversation with the administration and the legislature as we start to shift away from the current crises that we're dealing with. But the science is definitely going to be reflected in what we put out in the scoping plan. The 2045 reflects an executive order, but what you see in that chart in the ARB slide deck is that if we were able to stay on the same trajectory from 2030 or 2020 to 2030, we would actually be 10 years ahead on that 2050 80 by 50 scenario as well. So we've already been talking about if we're able to stay on the trajectory to hit the 2030 target, it gets us to 2040 per the latest science.
Thank you.
Thanks, Rajinder. So we are out of time for questions today. So if you didn't get to ask your question here, we encourage you to submit it in written form through the workshop docket. We will be posting a recording of this workshop likely next week. So at this point, I'd like to give Amber and Rajinder opportunities to give any closing remarks before we close the workshop.
This is Amber. I'll just say thank you all for your attention and your great questions today. I really appreciate it, and I look forward to reading the comments. And thank you to Rajinder and Maureen and Jordan and Matt for hosting this workshop and making this work possible.
Thanks, Amber. So this is Rajinder. I wanted to restate again that we've been working on carbon neutrality workshops since January 2019. The reason we've been having these workshops and introducing different topics is because when you look out to 2045 and you start to think about the kinds of transformation that needs to happen, it's dramatic, and it's going to take thoughtful planning. It's going to take a lot of input and information from people who are experts in the energy sector, what's possible in the industrial sector, and even what's possible when we think about maximizing all of the co-benefits, especially air quality in the vulnerable communities that we have. And so, you know, this is our way of trying to put some numbers and modeling around the scenarios of what we think we need for the future. It's not the exact future that we're going to be using in the scoping plan, and it's meant to just start that conversation. If there are other pieces of information, whether it's cost, technology, infrastructure, that you think would be important in this conversation as we move forward, we absolutely want to see that information, and we want you to send it to us. If there are studies that are underway that you think will be completed in the next year or so that can help on some of this, we definitely want to hear about those as well. 2045 is a long planning horizon for the next scoping plan. And we do have the luxury of doing that scoping plan update every 5 years. But if we're going to put ourselves on track to hit 2045, we fully recognize that there are actions that we need to start taking in the next few years to get to that 2045 target. And we want to make sure that we have the best information and that we as policymakers are putting out the right signals. We're designing our programs effectively to put us on track to what we need to have investments and action occur today, so that when we get to 2045, we look back, we actually have been making that incremental progress in realizing that 2045 or 2040 deep decarbonization that we want to have happen for California. The other thing I'd stress is we're not doing this in isolation. There are carbon neutrality targets in other states. There are carbon neutrality targets in other jurisdictions. And we are collaborating with many of those other governments to understand what they're looking at, what efforts they have. The report that E3 put out looks at efforts in Europe, and then it has the California context. So while there is a huge transformation that needs to happen, we are not alone. But we also recognize that in addition to seeing what other governments are doing, we need to make sure that all of us here in California, whether it's academia, investments, whether it's energy companies or technology companies, we are all working together to realize the future that we want to see. And so really appreciate everybody that put in their time and energy to participate in this, and we look forward to seeing your comments. We will continue to have some more workshops under the carbon neutrality banner, but early next year, we will be switching from this phase of carbon neutrality topics to the formal scoping plan, and there will be a kickoff workshop with several state agencies participating in that kickoff workshop, which is what we do for every scoping plan. And with that, I will turn it back over to you, Jordan.
Thanks, Rajinder. So Amber, we appreciate E3's work on this report and your participation in this workshop. So with that, we will go ahead and close the workshop. Thank you all and have a great day.
Thank you.